Hi everybody. So in today's video we're going to be talking about the second major theorem of this year. The second major theorem is called the mean value theorem. And we need to remember that in math the word mean always refers to average. What the mean value theorem does is it compares the average rate of change with the instantaneous rate of change. So in other words, it compares the regular slope with the derivative. And here's what it says. As long as you meet these conditions, these are like the if part of a theorem. As long as f of x is continuous, everywhere on your interval, including the endpoints. And as long as f of x is differentiable, everywhere on your interval except maybe at the endpoints, then we can say, this is the conclusion, the then we can say that the derivative of your function at some number between your endpoints has to equal the average rate of change between those endpoints. So to describe the average rate of change, we usually write f of b minus f of a all over b minus a. So the instantaneous rate of change, the derivative, at some number, has to equal the average slope. Now we saw this in our activity in class where we could make the slope of the tangent line equal the slope of the secant line as long as our function was continuous and differentiable. Now, we use the mean value theorem when we are trying to guarantee that the function has a specific slope value. We use the mean value theorem if we're trying to locate the place where a function's average rate of change is the same as its instantaneous rate of change. And it's also really important to know when we're allowed to use this and when we're not. So we're allowed to use the mean value theorem as long as we're continuous everywhere, including the endpoints. That means everything is connected, including having closed circles at the endpoints. And as long as we're differentiable, meaning there are no corners, cusps, vertical tangents, or discontinuities, except possibly at the endpoints. So if there was a vertical tangent right at your endpoint, that would be okay. So let's take a look at a few examples of what you might be asked to do with the mean value theorem. The first example says, given the function f defined by f of x equals 1 minus x cubed, what are all the values of c and the closed interval between 0 and 3 that satisfy the conditions of the mean value theorem? The first thing you need to notice is that, number 1, f of x is continuous. And the reason that I know that it's continuous is because this is a cubic function. If I picture a cubic function, it looks like this. It's never going to have any discontinuities like an asymptote or a hole or a jump. The second thing I need to note here is that f of x is differentiable. What that means is that there are no corners, cusps, vertical tangents, or discontinuities because, again, it's a cubic function. I know how those functions look. I've looked at them lots of times. So as long as I satisfy those conditions, then I can say that the derivative at some number has to equal the average rate of change. Now, the average rate of change over this interval would be f of 3 minus f of 0 over 3 minus 0. And what this is asking me to do is to solve and find the values of c that make this equation work. So let's see if we can do that. The first thing I would do is I would take the derivative and plug in c. So to take the derivative here, I would use chain rule. I would start by ignoring the inside, and I would drop the 3, leave the inside alone, and change that to a squared. And then I would do the chain, so the derivative of negative x would just be negative 1. Then this has to equal, if I start doing some computations here, f of 3 means plug the number 3 into here. So I would have 1 minus 3, which is negative 2, and negative 2 cubed is negative 8. Then I would have 1 minus 0, which is 1, cubed, which is 1, over 3. Lastly, I would take the c and I would plug it in for this x. So my simplified left side of my equation would be 3 times negative 1. I'm just going to move that to the beginning and make it a negative 3, parentheses 1 minus c squared. Now this has to equal the simplified side of the right side. So negative 8 minus 1 is negative 9 divided by 3, which is negative 3. Here I've created an equation that is solvable using algebraic techniques that I learned way back in Algebra 1. So I'm going to solve this equation now by just manipulating the function. So I would divide by negative 3 on both sides, which means I would have 1 minus c squared equals 1. I would square root both sides, and so I would have 1 minus c equals plus or minus 1, because when I square root, I always get two answers. So I would get negative c equals negative 1. I'm subtracting the 1 on both sides, plus or minus 1. Now, negative 1 plus 1 is 0, and negative 1 minus 1 is negative 2. And finally, when I divide by a negative, 0 divided by a negative is still 0, and negative 2 divided by a negative is positive 2. So if I look at my c values that I found, those I need to now just check to see if those are within the interval that I was supposed to look at. I was supposed to look between 0 and 3. Since both 0, which is included, and 2, which is in between 0 and 3, are in between there, both of these values would be my answer. Now, if either of those values were not within my interval, I would just say this is an extraneous solution. It doesn't count in this particular problem because it wasn't within my interval. All right, let's take a look at another question. So the next question says, applying the mean value theorem here between 0 and 2 guarantees that there exists some value c where c is between 0 and 2 such that g prime of c equals. Now, what they're asking me in this question is instead of finding this c, what would my slope have to equal? So you'll notice here my slope had to equal, my derivative slope had to equal negative 3 because that was my instantaneous slope, had to equal my average slope. So in other words, what does my instantaneous slope have to equal? Well, my mean value theorem says my instantaneous slope has to equal my average slope, g of 2 minus g of 0 over 2 minus 0. So if I compute that, g of 2 would be 3 times 4, which is 12, plus 2 times 2, which is 4, plus 1. And g of 0 would just be 1, all over 2. And if I simplify that a little bit more, I would have 16 plus 1 is 17, minus 1 is 16, over 2, which is 8. So my derivative has to equal 8 somewhere. Now this time it's not asking me to figure out where that happens, it's just saying what would you have to equal. Let's take a look at another example. So in the next example, which is very typical of what they might do on like an AP test as well as the last example, how many of these functions do not satisfy the conditions of the mean value theorem? So we have to think back to what our conditions are. First, we have to be continuous on the closed interval. So that means on including the endpoints. If I look at the first function here, everything is connected except this endpoint. So this function does not satisfy the conditions, which is what I'm looking for. For the next one, everything is connected, including the endpoints. We're good. For the next one, everything is connected, including the endpoints. We're good. And lastly, we've got a discontinuity in the middle. We've got a vertical asymptote, so not everything is connected, which means this one does not satisfy the conditions. Okay, if I take a look at the second condition, f of x has to be differentiable in between the endpoints. So, in other words, no corners, cusps, vertical tangents, or discontinuities. Now, if I look at this second graph here, I can see that there is actually sort of a cusp or a corner going on there. I'm not sure which one, but it looks kind of like a cusp. If that happens, then this does not satisfy the conditions. Here, everything looks pretty good. It's not quite a vertical tangent. The tangent lines would still be diagonal here. So it looks to me like 3 of these functions do not satisfy the conditions. So I would say C. All right, for number 4, a function f is continuous between -2 and 2, and f of -2 is equal to f of 2, which is equal to 0. So they're telling you the y value when you plug in -2 is 0, and the y value when you plug in +2 is 0. If there is no c between -2 and 2 for which the derivative is 0, which of the following statements must be true? Now, according to the mean value theorem, f prime of c has to equal f of 2 minus f of -2 over 2 minus -2. It has to equal the average rate of change. In this case, f of 2 is 0, f of -2 is also 0, and so we get that our derivative has to equal 0. According to the mean value theorem, that has to happen. But this is saying this does not happen. This is a very common question on the AP test, it's a very common question that you're going to see in our class. It's basically saying if this theorem says that it has to happen, but you know that this doesn't happen, then what went wrong? Well, what went wrong is you probably did not meet one of these conditions that allowed you to make that promise. So, for example, for -2 to 2, the derivative is bigger than 0, is positive. Well, I don't know when it was necessarily positive. I just know it probably wasn't continuous or wasn't differentiable. Between -2 and 2, the derivative is always positive. Those are the same answers twice, so that's definitely not it. Between -2 and 2, the derivative exists. Well, if the derivative always exists, then it must be always differentiable, which means it must have always been continuous, which means this should have been true, so that can't be it. Between -2 and 2, the derivative exists, but the derivative is not continuous. Well, the derivative doesn't have to be continuous, it just has to be differentiable, it has to exist. Between -2 and 2, the derivative does not exist somewhere. Well, yeah, that makes sense. If the derivative doesn't exist somewhere, then your function was not differentiable. And if your function is not differentiable, then you can't make this statement. You can't make this promise. So whenever it tells you that the theorem is broken, you're looking for one of the conditions to be not met in that situation. Finally, this is a very common example of what looks like an FRQ on the AP test. The continuous function f is defined on the interval between -4 and 3. The graph of f consists of 2 quarter circles and 1 line segment. So we've got a quarter circle, and a line segment. Number 5 says, find the average rate of change of f between -4 and 3. Let's just start with that. So find the average rate of change. So to find the average rate of change, I'm just going to do f of 3 minus f of -4 over 3 minus -4. So f of 3 is -3. F of -4 is -1. And 3 minus -4 is 7. -3 plus 1 is -2 over 7. Now the second part of the question says, there is no point between -4 and 3 for which the derivative is equal to this average rate of change. So it's a lot like the previous question. They're telling you the mean value theorem doesn't work. The derivative does not equal the average rate of change. Explain why this does not contradict the mean value theorem. So the mean value theorem says you have to equal the average rate of change. Your problem says we don't equal the average rate of change. How is that okay? It can't be a theorem if it doesn't work all the time. Well, the answer is that your function is either not continuous or not differentiable between these two numbers. Now, it looks based on this picture like everything is continuously connected, but there's a corner here and a vertical tangent here. So if we're not differentiable, then we can't apply the mean value theorem. So what we would say is, this does not contradict the mean value theorem because f of x is not differentiable at x equals, it looks like the first place where I have a non-differentiability is -3, and the second place would be 0. And if we're not differentiable, we're not contradicting our theorem because our theorem doesn't actually apply. All right, thank you guys so much for watching. I know it's a bit of a longer video, but I hope that this helped to make sense of it, and we'll practice this when I see you again.